Hello students, good morning. I hope you all are safe and healthy at your home. Welcome in this lecture. We continue in our unit part 2 heterocyclic compound. In previous lecture we completed classification of heterocyclic compound. Now in this lecture, first of all, we see nomenclature of heterocyclic compound and their important of heterocyclic compound. Some important compound according to our syllabus. So, first of all, we see nomenclature of heterocyclic compound. Nomenclature of heterocyclic compound. First of all, in the numbering of heterocyclic ring, the heteroatom is always given number 1. Heteroatom is always given number 1. I further repeat, in numbering of heterocyclic ring, the heteroatom is always given number 1. Furthermore, when two or more, when more than one heteroatom is present in the same ring, they are numbered in order. If more than one heteroatom present, then numbering is given in order to, first of all, oxygen, sulfur, and then nitrogen. When more than one heteroatom is present in same ring, they are numbered in order oxygen, sulfur, and nitrogen. Thus, the numbering in ring is done that direction which gives the lowest number to the substituent, which are further arranged in the alphabetical order. Now, the name of monocyclic compound are derived by a prefix. A prefix for name, a prefix indicating the nature of the heteroatom present. Repeat. The name of monocyclic compound are derived by a prefix indicating the nature of heteroatom presence and ending by this a. Ending by a where necessary. As for example, oxygen, then oxa, oxygen, then oxa, sulfur, then thia, sulfur, then thia, nitrogen, then aza, silicon, then sila, silicon, then sila. Phosphorus, we write P, then phosphor. So when name of monocyclic compound are derived by a prefix indicating the nature of heteroatom present and ending by a, as for example oxygen, oxa, sulfur, thia, nitrogen, aza, silicon, sila, phosphorus, phosphor. When two or more of the same heteroatom are present, we see here for monocyclic compound. But when two or more of the same heteroatom are present, then the prefix is for two, di, tri, etc. are used. And as for example, dioxa, for oxygen, dioxa, for nitrogen, triaza, for sulfur, trithia, etc. are used. If the heteroatoms are different, and about and if we rearrangement of word give more space, so I write down below. If the heteroatoms are different, their order of citation start with the heteroatoms of as high a group in the periodic table. If the heteroatoms are different, then the order of citation start with the heteroatom of as high a group in the periodic table and as low an atomic number in that group. Thus, the order of naming will be first of all oxygen, then sulfur, then nitrogen, then phosphorus, then silicon, etc. And as for example, thiaza, it indicates S then N. Nitrogen, sulfur then nitrogen, So the heteroatoms are different. Their order of citation start with the heteroatom of as high a group in the periodic table and as low an atomic number in that group. Thus, the order of naming will be start from oxygen, sulfur, nitrogen, phosphorus, silicon, etc. As for example, thiaza, sulfur, then nitrogen. These are the main point. Now, Now we see the condensed ring system. We see rules for condensed ring system. The condensed ring system is named by indicating the number of carbon is indicated by number of carbon atoms with which the heterocyclic ring is fused, which the heterocyclic ring is fused. As for example, quinoline may be named as first of all we draw the structure of quinoline. In previous lecture we described as quinoline, this structure quinoline. For condensed ring system, named by indicating the number of carbon atom with which the heterocyclic ring is fused, so quinoline may be named as 2,3-benzopyridine. 2,3-benzopyridine. Benzene is fused with pyridine. So, if we break down this compound from here, and heteroatom number is start from here 1, 2, 3. So, this is 2, 3 benzopyridine. And for only pyridine, this is pyridine. So it is start from here number 1. 1, 2, 3, 4, 5 and 6. 1, 2, 3, 4, 5 and 6. Here we complete nomenclature of heterocyclic compound. Now, according to our syllabus, we have some important heterocyclic compound. So, we start synthesis of heterocyclic compound. According to our syllabus, we will discuss synthesis and properties of pyrrole, furan, thiophene, pyrazole, imidazole, or imidazole. Both are same. It is also known as glyoxam, oxazole, and thiazole. Indole, benzofuran, benzothiophene, pyridine, pyran, pyridiazine, pyrimidine, pyrazine, and in last quinoline, and benzoxazine. Benzoxazine. We will study this important heterocyclic compound in our video lectures. So we start with this type of important heterocyclic compound, and the chemistry of heterocyclic compound is a very vast subject, and it is not possible to discuss the whole of them. Heterocyclic compounds are very widely distributed in nature, and they are essential to life in various ways. Several of the important compounds contain heterocyclic ring are present in most of the number of vitamin B complex, most of the alkaloids, antibiotics, chlorophyll, hemine, other plant pigments, amino acids, dyes, drugs, enzymes, etc. So, these are very important for our life. First of all, we start with 5-member ring containing one heteroatom. That is our first compound, pyrrole. 5-member ring containing one heteroatom. Our first compound, pyrrole. Pyrrole. Chemically, we describe structural formula of pyrrole by this. Here double bond and formulae C4H5N 1 2 3 4 CH2 C4H5N. This is pyrrole. Pyrrole is the most important among all the 5-membered heterocyclic compound. Pyrrole nuclei occurs in the various important natural products, as for example chlorophyll, coloring matter of leaves. Green color is occur in leaves. It is from pyrrole. So, very important natural product, chlorophyll. Hemine, coloring matter of blood, we known as a hemoglobin. Berberine, coloring matter of bile. Some alkaloids, vitamin B2, etc. So, various important natural product which contains pyrrole. These are chlorophyll, hemine, that is in from hemoglobin, berberine, that is color matter of bile, some alkaloids and vitamin B2, etc. Natural compound contains pyrrole. Now, isolation of pyrrole. Pyrrole occurs in coal tar and bone oil. Pyrrole occurs in coal tar and bone oil and is generally isolated from the latter source. The oil is washed with dilute alkali and acid to remove acidic and basic substances respectively. The extract is now fractionally distilled. When the pyrrole distilled over in the fraction of boiling point, fraction in the boiling point 100 to 150 degrees Celsius, distill off at 100 to 150 degrees Celsius. And finally, it is purified by fusing with potassium hydroxide. The potassiopyrrole, the potassiopyrrole so form gives pure pyrrole on we here stated following method. So we see some of the basic methods for the synthesis of pyrrole. Number one, by passing acetylene and ammonia. Acetylene and ammonia, we have a structure CH triple bond CH. 2 moles of acetylene. Acetylene. With the help of ammonia, we write down NH3 as this, ammonia. So by passing acetylene and ammonia through a red hot tube, we get pyrrole. We get pyrrole. We get pyrrole. C4H5N, pyrrole. Now we see second method by passing a mixture of furan. Furan, we indicated furan. Structure of furan we discussed in classification. 5-member ring heteroatom as oxygen is known as furan. So by passing a mixture of furan and ammonia, that is NH3, and steam over at 480 to 490 degrees Celsius with the help of Al2O3, it converts into pyrrole. It converts into pyrrole, and Now we see third method. By distillation of succinimide. Succinimide. We write down structure of succinimide. C double bond O, C double bond O and attach NH. This is succinimide. And if we rearrange this compound, so it is written by this structure, and this treated with Zn dust, zinc dust, so we get pyrrole. Pyrrole. So by the distillation of succinimide, our zinc dust gives pyrrole. Now we see more example for preparation of pyrrole. Number 4. By distilling the ammonium mucate and glycerol at 200 degrees Celsius. Ammonium mucate first decomposes into mucic acid and ammonia. The former then undergoes dehydration, decarboxylation and cyclization by reaction with ammonia. So we start here from mucic acid. Fourth method, mucic acid. Mucic acid. And it is treated with ammonia, gives decarboxylation. Pyrrole. So by distilling the ammonium mucate and glycerol at 200 degrees Celsius, ammonium mucate first decomposes into mucic acid and ammonia, the former then undergoes dehydration. First of all, mucic acid dehydrated and decarboxylation and cyclization by reaction with ammonia gives pyrrole. Ammonia gives pyrrole. For pyrrole, we see one more synthesis. It is known as NOR synthesis. NOR synthesis. KNORR. This is the most general method for the synthesis of pyrroles and involves the condensation of an alpha amino ketone or alpha amino beta ketoester with another ketone having an active methylene group such as acetoacetic ester. So we see the synthesis. It is known as NOR synthesis. It is known as NOR synthesis. CH3 C double bond O CH2 NH2. CH2 C double O C2H5 C double bond O CH3. It is converted into cyclic compound. It is 2,4-dimethyl pyrrole. 2,4-dimethyl pyrrole 3 carboxylic ester. 3 carboxylic ester. It is known as NOR synthesis. This is the most general method for the synthesis of pyrrole. Synthesis of pyrrole. Now we see the structure of pyrrole. Structure of pyrrole. Pyrrole is a resonance hybrid. So we write down structure of pyrrole resonance hybrid. We indicated resonance hybrid in pyrrole. This is N minus. This is resonance hybrid of pyrrole. Pyrrole is less aromatic than thiophene and more aromatic than furan. That is the order of aromaticity of. For pyrrole we see thiophene. Pyrrole is less aromatic than thiophene and more aromatic than furan. So this is the order of aromaticity of pyrrole, thiophene and furan. Because of the contribution of the lone pair of electron of nitrogen atom to the formation of a 4n plus 2 pi electron molecule. The availability of this lone pair for protonation is very much decreased and consequently pyrrole is very weak base. So this is the resonance hybrid of pyrrole. Now we see some more properties. Pyrrole is a colorless liquid. Colorless liquid. State of pyrrole is liquid. Boiling point 131 degrees Celsius. But turns brown in air. In open air it is turned into brown color. It is sparingly soluble in water but readily in alcohol and ether. Pyrrole is a resonance hybrid. Its resonance energy is about 31 kilocalorie per mole. Due to lone pair of electron of the nitrogen atom is not readily available for protonation and hence the pyrrole behave as a weak base. Pyrrole is a weakly acidic compound due to the presence of iminohydrogen atom. This is iminohydrogen atom. So it is weak base. And hence it forms salt with alkali metal hydroxide. If potassium hydroxide, then potassium salt of pyrrole, calcium salt, magnesium salt of pyrrole. Now we see chemical properties. Electrophilic substitution reactions for pyrrole. The reactive nature of pyrrole toward electrophilic reagent is due to the fact that the pi electron density at the carbon atom of pyrrole ring is very high due to resonance structure as compared to that of benzene and hence pyrrole is very reactive toward electrophilic. Electrophilic substitution of pyrrole occurs preferentially at there of the 2 position followed by 3 position. So we see 2 and 3 substitution of pyrrole. First of all, we see 2 substitution of pyrrole. X and H. This is 2 substitution. Now we see 2, 3, 3 substitution. Third position. So this is 2 and 3 electrophilic substitution of pyrrole in 2 position followed by 3 position. Now we see various electrophilic substitution reaction of pyrrole for 2 and 3 position. 2 and 3 position. This is the last topic for pyrrole. This is pyrrole. Now we see different type of reaction for pyrrole. If halogenation takes place, I write down reaction of halogenation. Halogenation with the help of bromine and methanol. 2, 3, 4, 5 tetrahalo. 2, 3, 4, 5 tetrahalopyrrole presents. 2, 3, 4, 5 tetrabromopyrrole. If we treated chlorination, then tetrachloro, tetraiodo, tetrafluoro compound is present. If second reaction, if we treated it as a nitration, NO2 plus nitration, then 2-nitropyrrole. 2-nitropyrrole is formed. If sulfonation takes place, SO3H plus sulfonation takes place, then sulfonyl group present and number 2, position 2, SO3H, and its name is pyrrole 2-sulfonic acid. This is 2-nitropyrrole. And this is pyrrole 2 sulfonic acid. Pyrrole 2 sulfonic acid. This is sulfonation. If we treated pyrrole by acetylation, F and C reaction, Fiedel and Kraft reaction, acetylation, then 2-acetyl-pyrrole, COCH3, 2-acetyl-pyrrole is formed. If we treated as a carboxylation with the help of carbon tetrachloride and KOH in presence of carbon tetrachloride and KOH, then pyrrole 2 carboxylic acid is formed. Pyrrole 2 carboxylic acid is formed. This is pyrrole 2 carboxylic acid. If we treated Kolbe reaction, Kolbe reaction, Kolbe reaction in presence of CO2 at 160 degrees Celsius. So, pyrrole 2 carboxylic acid is produced. Pyrrole 2 carboxylic acid is produced. If we treated formylation, formylation with the help of HCN HCl mixture, hydrogen cyanide and hydrochloric acid, and then hydrolysis gives pyrrole 2 aldehyde, pyrrole 2 aldehyde, CHO group introduced at fourth position. Introduced at fourth position. So this is the different types of reaction with pyrrole. If we take reduction, we have one more reaction. Reduction takes place with the help of zinc dust and acetic acid. Zinc dust and acetic acid. Then pyrroline is produced. Pyrroline. This is pyrroline. Rearrange board for better structure. Pyrroline. And if we take one more reaction as a oxidation process takes place. I have space here. Oxidation. Then it is converted into melamide. Maleimide. Melamide. So when oxidation takes place with the help of chromic acid, CrO3 and H2SO4, with the help of CrO3 and H2SO4 gives melamide. So these are the very important reactions of pyrrole. We here stop our this lecture. Okay, thank you.